Hi everybody! In this video I'll be presenting Reviving Unsupervised Optical Flow. This is a WACV 26 paper. My name is Azin Jahedi and I hope you find this paper useful. I'll start by defining optical flow. If we have two consecutive images in an image sequence, for example image 1 and image 2, we want to compute the motion field between the two images. From image 1 to image 2, that would be the forward flow. This flow shows where each pixel from image 1 moved to image 2. And you can see a visualization of optical flow where different hues show different orientations of motion and saturation shows the flow magnitude. The optic flow that we just defined has many applications in different domains, for example, autonomous driving and video compression. So a method that could adapt to different application domains would be useful. While supervised methods achieved impressive accuracy, they normally don't generalize that well to new domains. And collecting ground truth optical flow to train them is also not easy. In this case, unsupervised methods are attractive. Now, the majority of unsupervised methods are still based on older architectures like PWCnet. And although RAFT caused a paradigm shift in supervised optic flow, its use in unsupervised flow is very limited. SMURF, as the only state-of-the-art RAFT-based method, requires extensive resources for training and is not easy to reproduce. It looks like unsupervised optical flow methods have not reached their potential, and progress in this field has become limited. Therefore, an open-source state-of-the-art RAFT-based method would be useful. So in this paper, we do a few things. We reinvestigate unsupervised training strategies to find effective settings and present two unsupervised methods: simple unsupervised RAFT or SunRAFT and multi-scale unsupervised RAFT or MoonRAFT. We also fully open source our PyTorch code. Now, let me briefly go over unsupervised training objectives and then we can talk more about our approaches. We use three main unsupervised objectives. The first loss is a photometric loss that shows how visually close two pixels are. We use the ternary loss of census transformed images from OnFlow. This loss uses neighborhood information by computing the order of gray values in a window. Because of this, it is stronger than just comparing pixel values, and it's also more robust against illumination changes. Now what we do is to backward warp the second image with the current forward flow, and if the flow is accurate, the correspondence is brought back to the position of the reference pixel, and they should be visually similar. Of course, in this case, occluded regions are masked out. Our methods employ edge-aware first or second order smoothness terms as regularization, similar to UFlow and SMURF. The point is to reduce the jumps in the flow field where there are no edges in the reference image, and in this case, the edge detection is rather basic. Note that in scenes with a lot of ego motion, like driving scenarios, we use second-order smoothness term, like in SMURF and UFlow. Last but not least, we can talk about the self-supervision objective. And here we have two optical flows: the student flow and the teacher flow. The student flow is computed from augmented image pairs. And these augmentations are photometric, occlusion, and geometric transformations. And the teacher flow is computed from unaugmented or clean images. And then it's transformed according to the geometric augmentations that we used on the input of the student. You can see the equation here. Note that we apply the self-supervision only in places where the teacher is forward-backward consistent and the student is not. After computing each of the loss terms I discussed for both directions, forward and backward, we sum them up. And we have three loss terms, and the full loss is shown here. For SunRAFT, we have one scale only with 12 recurrent iterations. For MoonRAFT, we have 3 scales and 4 recurrent iterations per scale. Let's now talk about what is different in our approach compared to SMURF. The first aspect is the self-supervision settings, where we apply photometric, occlusions, and diverse geometric augmentations. And this is unlike DDFlow and SMURF that follow a fixed zoom and crop transformation for self-supervision. Also, as mentioned before, we only apply self-supervision where the teacher is confident and the student is not. While SMURF shows a positive impact of removing this mask, we found it effective in achieving more accuracy. We also apply more weights to the estimate of early iterations. As each intermediate flow impacts the estimation of the next iteration, it is important to provide sufficient supervision to them as well. We also don't perform full image warping because our ablations showed that it was not helpful in our case. Finally, we also reinvestigated the training schedule and weight initialization. For chairs, our training schedule is the same as SMURF, but for both Sintel and Kitty, we use a shorter schedule. We also found out that Raft's weight initialization yielded a more stable training than the initialization used in SMURF. Using the settings I discussed, we introduced two methods. The first one is simple unsupervised raft or SunRaft that can be seen as a two-frame and a simpler alternative to SMURF, which achieves new state-of-the-art for two-frame unsupervised optical flow. The second one is MoonRaft, which is the multi-scale version of SunRaft. It is based on the MS-Raft method and has a novel upsampling component. As you all probably know Raft, I skip its architecture, but for completeness I show MS-Raft's architecture. This is the architecture of MS-Raft. You can see that the flow is estimated in a coarse-to-fine manner. Now, to compute the flow at full resolution at each scale for computing the loss, after using the ×2 convex upsampling of Raft, bilinear interpolation was used. Interestingly, unlike in the supervised case, using MS-Raft's architecture that we just showed did not yield improvements compared to using the single-scale Raft. The problem is that using MS-Raft's procedure, the loss is computed from flow fields that have been compromised with large factor bilinear upsampling operations. So we want to compute the loss now from high-quality intermediate and final outputs. To this end, we introduce a gradual context-based upsampling. Since flow edges typically align with object boundaries in the reference frame, context features as representations of the reference frame are a suitable source of information to lead the upsampling process. We add learnable components to the unit style feature encoder of MS-Raft to compute these context-based upsampling masks, and we compute them in 3 different scales. They are later used for upsampling the flow gradually to full resolution. Here you can see how those 3 masks are used in our gradual convex upsampling procedure. Here CU1 denotes the first context-based convex upsampler that uses the mask from 1/8 resolution I just showed. Then the second mask is used to upsample the flow from 1/4 to 1/2 resolution, and finally the last mask upsamples the flow to full resolution. Let's now compare the results of bilinear upsampling for the coarsest scale to full resolution to our upsampling. Here you can see the results for bilinear upsampling. And this is the result of using our gradual context-based convex upsampling. You can see clear improvements with our upsampling procedure. This modification is important in enabling this multi-scale architecture to achieve state-of-the-art results in the unsupervised case. Let's now compare results to the current state-of-the-art. Both our methods outperform the multi-frame SMURF method on Sintel Clean with only 3 recurrent iterations. For MoonRaft, that means only 1 iteration per scale. Let's look at more results. MoonRaft's results on Sintel Clean after pre-training on chairs is on par with SMURF after fine-tuning on Sintel. Both our methods achieve a new state-of-the-art for 2-frame unsupervised optical flow on Sintel, with MoonRaft outperforming the current multi-frame state-of-the-art by 28% on Sintel Clean. Besides, SunRaft is also state-of-the-art on Kitty. Now, to sum up, we presented reviving unsupervised optical flow, where we reinvestigated unsupervised training strategies to find effective training settings. We presented SunRaft as a 2-frame and a simpler alternative to SMURF. We also presented MoonRaft as a multi-scale extension of SunRaft, where we introduced a novel gradual context-based convex upsampling. Both our methods achieve state-of-the-art results on Sintel. SunRaft also achieves state-of-the-art results on Kitty. And finally, we open source our PyTorch code for the community for further developments in the field. Thank you for watching, and I hope you find these methods useful.